Hi, this is Mick Elliott from Electronics Specifier. I am here on the Rohde Schwarz stand where they are promising you can measure the impossible. And you measure the impossible with the FSWX network analyzer. And with me is Florian Ramian, measuring applications at Rohde Schwarz. And he's going to talk us through some of the features of this product. Ramian, over to you.
Yep, thank you, Mick. So we're looking here at the FSWX, which is the world's first dual-channel signal and spectrum analyzer to fully phase-coherent input path. And what we're looking here at the demo is a component testing setup. We're looking here at an EVM measurement. We have a 32 APSK signal that's running through power amplifier. We can already see a constellation diagram. We can see an EVM, and we can see there is some distortion happening. I'm going to go deeper inside. So this is a standard measurement, but we want to go deeper inside, and what we can do, or what we mean with measure the impossible, is make invisible what has been hidden so far. At first I'll switch the applications because we're measuring a power amplifier, so we want to distinguish the distortions. It's still in single channel operation mode, but it already shows nonlinearities, differentiates that from frequency response and noise contributions. If you're remembering the EVM numbers, it's roughly the same EVM now here that we had in the vector signal analyzer display. But now we'll go to the dual channel setup. So instead of measuring my whole demo setup here, I will now focus on only what's the DOT. And in order to improve the measurement accuracy, what I'll do is I'll directly compare the output of the device on the test to the input of the device on the test. And that's where I need my two channels.
Right, okay.
All right. So what I'll do now is I'll turn on the dual channel measurement. And just in case you're remembering the EVM numbers, you can see a significantly improved EVM, which basically means in this scenario, the number I have been measuring before was not only the device on the test, but the device on the test plus the measurement setup. And that's what I can exclude from my measurements now with my two-channel approach. So that's typical power amplifier characterization measurement with two channels directly comparing the output to the input. However, we have a lot more fancy measurements that we can run because, as I mentioned in the very beginning, the two channels are fully phase coherent. Which means that I can now run measurements that have so far not been possible on a signal analyzer. I can, for example, run a group delay measurement on a fully modulated signal. And as we can see, it gives me, we have round about 5 nanoseconds group delay through my device on the test. Also, something new is on a standard signal analyzer, we're not looking at absolute phase because it has no meaning. However, when we have a phase coherent dual channel analyzer, I can switch it into absolute phase mode. And that, you can see it on the display, gives me an absolute phase number, which is the phase difference between the two channels. So being able to measure the output or compare the output of a device on the test directly to the input, and at the same time measure absolute phase and group delay is a unique thing for a dual channel analyzer.
Florian is now going to talk us through the spectrum analyzer part of the instrument. Away to you, Florian. Yep.
All right, so we've discussed the PA characterization setup, and now I'm going to show also a very new feature that requires a dual channel architecture. I have switched over to a standard spectrum analyzer measurement. So this is an ASLR measurement. And what I'm showing here is the advantage that you can get from cross-correlation. Cross-correlation is a known feature, for example, from phase noise testers. However, we have introduced it in spectrum analyzers and also in the signal analyzer domain here. What we can see on the screen is in yellow, it's a standard RMS ACLR measurement. And as you can see in the center part of the screen, we have the signal and the non-linearities. That's really a signal coming from the outside of my instrument. However, when you move to the very right or by the left-hand side, usually my instrument starts contributing in terms of wideband noise. And this is where we can, by using cross-correlation, improve the dynamic range of the measurement. And what we have added is a new detector type called RMS cross-correlation.
Okay.
And as you can see, it's activated in trace 2, which is or corresponds to the blue trace here. And if you just look at the very right-hand side here, you can see an improvement of around 10 dB in dynamic range at a very moderate increase in sweep time. So you can see the numbers updating, which means the measurement is up alive, and we're talking about measurement times of a few seconds here, and we're talking about a dynamic range improvement of around 10 dB. So the cross-correlation feature and the dual channel feature, that's basically the brand new things on the FSWX.
Okay, and this is 5G.
That's the signal we are looking here is still, it's the 32 APSK signal, but it could be anything. So whatever signal you want to use for testing your device, it's okay. Actually, in the dual channel scenario, you don't even have to know what it is, because we do measure live the input signal to the device under test.
Okay. I think this was announced maybe a month or two ago. What's been the reaction from the customer base so far? Because it is something a bit different for this part of the market. Yeah.
And I think there's different reactions. We have reactions, wow, that's the thing I have always been looking for. Mm-hmm. And then also we have had customers saying, oh, that's very interesting. What do I do with that? So we're trying to showcase what we think are good applications, but I'm very sure there's a lot of applications we haven't even thought about yet.
Okay. Florian Ramian, thank you very much.
Thank you.